Hi everyone, I'm Robert Lilow. I'm a postdoc at the Technion in Israel, and I'd like to talk about how you can reconstruct the density and velocity fields in the local universe using neural networks. And more importantly, how these neural networks are related to well-understood statistical estimators. Most of what I've shown today can also be found in this paper, and this is work that has been done together with Punyakoti Gandeshaya-Vena and Adi Nassar. So let me first start with a little motivation for why we actually want to reconstruct these density velocity fields. Because usually you think about constraining cosmology using statistical properties like a power spectrum, but actually there's complementary information in the 3D fields themselves. So I'll give you two examples. First, I'm looking here at the continuity equation in the linearized form, so which says that the negative diversion of the velocity field is just directly proportional to the overdensity delta with proportionality given by the growth rate f. So the larger f is, the faster matter accretes onto an overdensity. So if you now take a galaxy survey, reconstruct the density, and via this or its relation or its nonlinear version, the velocity field, then you can compare these peculiar velocities that you reconstruct to observed ones, for example, from the Tyler-Fisher relation, and this way constrain the growth rate and therefore also omega m. Another application is in the local measurement of the Hubble constant. So if you compute the Hubble constant from supernovae, you compare the supernovae distances to their redshifts. But of course, you want to compare them to the cosmological redshifts, which for nearby supernovae and low redshifts you have to take into account peculiar velocity correct contribution to that. Otherwise, you will introduce statistical as well as systematic errors. And the most recent analysis of Shoes and Pantheon Plus take this actually into account and find that this makes a notable difference. All right, so now you have some ideas of why this is useful. Why would I want to use a neural net for that? So let me start with giving a big picture description of traditional inference methods. There you have two ingredients essentially. You have the data that you observe, galaxy number count, and you have some model, for example, your prior, your likelihood, etc. You put these together, and from those you compute some statistical estimate, some mean or some maximum likelihood to give you a reconstruction of the signal. Now, this has the big advantage of giving you a lot of control over what actually enters your model that relates data and signal. But at the same time, the flip side is that you usually have to do some simplifications in your model to actually compute this. Or if you want to get more and more sophisticated with this model, quickly this approach becomes numerically extremely expensive. So this is when neural networks have a different approach in the context of machine learning and can maybe help. So there you flip around these inputs and outputs of the schematic, and both data and the signal matching that data, these are the inputs to your machine learning process. So based on these, your neural network parameters are optimized to find the optimal mapping between the two, and while this implicitly learn all your model characteristics like the prior, the bias, etc. So if the input data you use is of sufficiently high fidelity from embodied simulations matching the correct survey characteristics, you can learn very, very sophisticated mappings quite easily and efficiently, because the training process doesn't take much resources. In fact, everything I'm showing today was trained within 1 or 2 hours on a single GPU. But of course, the big question is always, can we actually trust the results of a neural net? And while I can't answer this question comprehensively, I at least want to describe some insight, some interpretation of what a neural network does that helps build confidence in the results. And what I'm going to show now is essentially textbook knowledge from a machine learning point of view, but I guess it's not widely enough known in our community, so it's worth pointing this out. Namely, that once you specify the function that you want to minimize, the loss function, and in your network architecture, you can essentially prove mathematically what kind of estimate your neural network should find. So what I'm using here today is the most widespread loss function, the mean squared error. So for each sample of your training set, you compute the neural network estimate of the signal given the data, and then you average the squared error of this over a sufficiently large set of training sets. And then update the parameters of your neural network by minimizing this quantity. Now, if you look at the simplest neural network first that you could imagine, just an input layer, an output layer, say galaxy number counts and velocities, connect all of them just in a linear fashion with weights and biases, so the whole network just describes a big linear mapping, then it's a very simple task to find the values of W and B that optimize this loss function. What you will find is this combination of signal and data covariance matrices, which many people recognize as the familiar Wiener-filter, which is a very widely used and robust linear filter. And this makes sense because the Wiener-filter is the linear filter that minimizes the variance between signal and reconstruction, which is just the MSE. Okay, good. So the backbone of any neural network is essentially equivalent to a Wiener-filter. Now, a full nonlinear neural network, of course, is different. But we can still repeat this exercise. We still assume the same mean squared error, but just generalize the argument for finding the optimum by not assuming a specific shape. We find this expression, and just after a few manipulations, you quickly see that a general nonlinear network should find the mean of the posterior of your signal given the data. And that's a very powerful estimator, since this posterior can be arbitrarily complex and non-Gaussian. Also, with traditional methods, it's very expensive to compute, usually involves averaging over many Monte Carlo samplings. So that's excellent. That is a meaningful estimate that we can compute efficiently using a neural network. But of course, we have to make sure that our network is sufficiently complicated, sufficiently expressive to actually represent this estimate. And in this work, we use so-called unit autoencoder architecture, which has proven itself in many applications. It's essentially three main ingredients. We have this left branch, the encoder. It's a series of convolutions and with pooling, that is coarse graining steps in between, where you always group nearby points on your grid. And this way, each deeper level helps you in encoding the relevant information of your input and also gives you access to more larger and larger scale information. Then afterwards, you essentially have a reverse architecture to get you back up to the resolution of your output fields that you desire. The third ingredient, or unit, are these skip connection between these two branches, which help preserve the spatial information in your input, which would easily get lost if you have to go through the source structure always. Now, the first thing we did with this network is do a little cross-check where we applied to completely Gaussian fields. So we have a Gaussian random field as our true input. We add some additional noise, Gaussian noise, to have a Gaussian observed field, and then compute both the autoencoder and the Wiener-filter estimates. The thing is, in this case, for Gaussian field, we know the mean posterior is exactly the same as the Wiener-filter, so they both should match, and in fact, they do. Visually, they're indistinguishable. And also, if you look at a scatter plot, especially this little inlay plot, delta autoencoder versus delta Wiener-filter, they have a one-to-one correspondence up to negligible numerical noise. Excellent. It sounds like a trivial task, but I think it's important. I want to make sure that if you apply this very complicated nonlinear network to the Gaussian fields, where you know the solution is just a linear mapping, it better reproduces this linear mapping and doesn't hallucinate some complicated nonlinear reconstruction. But as you see here, it doesn't, it's consistent. Now to the more interesting case, the non-Gaussian fields. So in this application, we choose rather simple setting for mock fields, which is sufficient for what we want to show. We have this small periodic box with a 128 cube grid of both the density and velocity fields, which we both compute with second-order Lagrange perturbation theory, which is good enough for this for the tests we did here. The galaxy data are obtained by Poisson sampling, assuming a typical mean galaxy density for a local survey. And we consider redshift space distortion to be along just the z-axis, not the actual radial direction. And in total, we used 1,000 realizations. Now, in the setup, let me first look at the density reconstruction. So if you look at the lower left panel here, this is the true 2-LPT density we would like to reconstruct. Up here is the Poisson-Sambert galaxy distribution that we use as an input. Then in these two columns, we have the autoencoder and Wiener-filter reconstructions. Let me first focus on these two lower panels. You can see both of them nicely capture the large-scale features of the true density, but you can see significant differences at small scales, where the autoencoder actually nicely captures these fine filaments, whereas the Wiener-filter fails at that, becomes rather blobby. It doesn't have all the higher order correlation information needed to reproduce that. So you clearly see the improvement obtainable with this autoencoder. And the difference between the upper and lower panels is just if you include retrospace distortions or not in our observation. But as you can see, visually there are small differences, but it's not very obvious. However, you can see it more clearly now from looking at the mean squared error as a function of our training epochs. So let's first focus on these lines down here, the solid lines. Red is the loss function computed for the training sets we actually use for the minimization for loss function. And the green is a separate validation set to make sure that we're not overfitting to our training samples. And as both lines line on top of each other, that's not happening. Excellent. Also, we have a nice and stable convergent behavior, and overreach consistent 15% improvement over the Wiener-filter. For the retrospace distortion case, it's a similar picture, just overall slightly worse reconstruction accuracy, as you would expect. Excellent. And now we can look again at the scatter plot between the true and the reconstructed densities, where you can see notable difference to the low density regime again. However, what I would like to point out more actually are these crosses and triangles. So what I did here is to actually check the properties. So if the properties of a mean posterior estimate are satisfied by our autoencoder estimator. So this is always, each of these points is the mean of the true fields in a bin of a given reconstructed density value. So for the mean posterior, this thing should by definition exactly be the same as the estimate. So should fall on the 1-to-1 line. As you can see, that actually nicely happens for our autoencoder. It really matches our expectation of the mean posterior estimate, whereas the Wiener-filter, which doesn't do this for these non-Gaussian fields, shows these deviations here and more starkly at low densities. So that's an excellent confirmation of the behavior of our neural network estimate. And now we also repeated the same thing for the pure velocities. So here I'm showing in the upper panels the velocity in Lagrangian space, the lower panels in Eulerian space. Lagrangian space is interesting because there's a more nonlinear mapping between data and signal, also is relevant for initial condition reconstructions. And for that you can see, while neither of the two estimators are able to capture all the fine details, still the autoencoder captures much more of the intermediate scale features than the Wiener-filter does. And in the Eulerian case, well, there the true field itself is already much smoother, so the difference between the two estimators is not as pronounced. But still, if you look at the contours, you can see that the autoencoder is much more accurate. And this is confirmed by the mean squared error for the velocity fields, which essentially paint the same picture as for the densities, although the relative improvement can be even larger. Excellent. And lastly, for the velocities, we also look at the scatter plot, which in this case looks really similar for both of them. But if you look at these bint true values for given estimated value, you can clearly see that the Wiener-filter, like for density, deviates from the 1-to-1 line, specifically at large velocities, whereas the neural network stays close to the 1-to-1 line as a mean posterior estimate should do. So again, this works out. So last thing we did in this paper was then to check what happens if we mask part of the data, as you would have in the real survey. So we masked like a 40 megaparsec wide slab approximately throughout this box, and then looked at a reconstruction in and around this masked area, marked here by the black lines. As you can see, visually on the field level, look very similar, and the same you can see here quantitatively at the MSE. Now not a total MSE, but the MSE in individual slices parallel to this mask. So this area in the middle is the masked area. And as you can see within the MSE of both are similarly high, and in fact they just match the cosmic variance. That's because inside the mask there is not really any density information to be gained. For this, the correlation length in density field is way too short. So the best guess is just the mean cosmic variance scatter around it. And yeah, also a neural network can't do magically better, and in fact, it shouldn't. However, what is very important to see is outside of this mask, the neural network still reproduces the same low MSE as it did without any mask whatsoever. So it means the introduction of the mask, breaking some symmetries, doesn't suddenly hinder our training process. Still works fine. I have a similar picture for the velocities, although there you can actually see a notable improvement of the autoencoder over the Wiener-filter within and around the mask, both visually as well as the MSE. Just in the middle, very center of the mask, they become similar. And here the reason is that the correlation length in the velocity field is much larger. So you actually have information about the velocity propagating further into the mask, and the autoencoder correctly captures this information, as you would hope. And then before I conclude, I just want to quickly show you something that goes beyond this paper, some preliminary results where we drop many of the simplifications of this first tests and create mocks that are actually representing real survey properties. So instead of 2IPT, we actually use full n-body mocks based on the photo simulation suite by Velasquez-Navarro et al. We put the observer in the center and have the retrospace distortions properly in radial directions. We also impose a selection function that mimics a flux limit of the survey, so where you have fewer and fewer galaxies visible at larger distances, and these are also sampled with a galaxy bias. And as you can see, since this is quite harder task to reconstruct this true density from this observation, the overall quality of the reconstruction is lower than for the simpler case I showed before. But what you can still see is that the consistently more coherent and improved reconstruction of an autoencoder. So you have fewer artifacts, and you overall have a sharper, more small scale features than the fuzzy Wiener-filter. And we can quantify this again by looking at the MSE. Now in shells with increasing radius from left to right. So you can see overall the reconstruction error increases towards the boundary just because galaxies become much faster, but crucially, the autoencoder is consistently better than the Wiener-filter. And with this, I would like to conclude. While traditional reconstruction methods have more control over their model, they unfortunately often have to simplify it or are very expensive otherwise. A neural network can learn these properties of the model very efficiently from high-fidelity simulation-based mocks, and gives you an efficient way to compute a powerful mean posterior estimate, which consistently improves over the widely spread Wiener-filter. The obvious next step is to apply this to real data. Thank you.